Okay, welcome to the first official video in the Principal Component Analysis tutorial. Here we're going to formally introduce the PCA. So at its heart, PCA is a dimensionality reduction algorithm, but it can be useful as a tool for helping with visualization, for filtering noise and redundancy out from the data, and also for extracting latent features that might exist in the data. It's going to do this by providing a low-dimensional representation of the data containing as much of the variation in the data as possible. Now, when you hear this word variation, you should think variance, the second moment of a data set. So the variance is the representation of the spread around the mean of a data set. And we're trying to capture as much of that variance as possible. So if our original data is n observations in p dimensions, so an n by p matrix, PCA is going to be very useful when not all of those p dimensions are equally interesting. So when not all of those p dimensions, when not all of the variance in those p dimensions is relevant. And what we're going to do is try and create a small number of dimensions that contain as much of the interesting variation as possible. So mathematically, the way this is going to work is by creating new columns that are linear combinations of the original columns. So here we've got x1, x2, x through xp that are the columns of data in our matrix. And we're going to create new columns, so z1, z2, z as many as we want, hopefully less than p, where each of these z columns are some number times x1 plus some number times x2 plus all the way up through some number times xp. And we're going to do this to create, z1, z2, and hopefully just a few of these z components that capture as much of the variation in the original data set as possible. All right, so let's go ahead and make this a bit more concrete by running some code. So we're going to start to visualize this by thinking about a two-dimensional data set. So we've got that right here. We've generated some random data along in 2 dimensions. And just by looking at this, it's pretty clear that there's some linear relationship between the x-axis and the y-axis, between x and y here. Now, you might be thinking, well, let's use regression. But remember, we're not seeking to predict a y value from the x value. We're doing an unsupervised problem here. What we're seeking is a relationship between x and y. So we're going to use our old friend scikit-learn to do this. We're going to get the PCA model from the sklearn.decomposition module. And I'm going to instantiate a PCA model with 2 components and then fit it to the data. So we've done that. And we're going to have a look now at 2 aspects that are generated by this principal component analysis. So the first is the actual principal components that were generated. And what we've got here are 2 vectors that represent axes along which the variation is most interesting. This is going to make more sense in a moment when we visualize it. But each of these is our principal components. We have 2 of them. And you're probably saying to yourself, but we had 2 components already. So what's interesting about this? Well, if we have a look at the explained variance, we can see that the first component, this component right here, explains 76% of the variation in the data, which is, for a principal component, an extremely large number. Most of the data was captured in a single component, and this is what we're talking about. We've taken data that was in 2 dimensions, and we're going to be able to represent it in a single dimension. And you can see that the second component only captured 2% of the variation, and then it looks like we lost 20, 21%, 22% of the variance in the data we lost to noise. And that's okay. That's going to happen. We're doing predictive modeling here, and it's not going to be perfect. All right, so let's go ahead and visualize these to get a better sense of what we're talking about here. So we're going to visualize the original data that we start with. and then we're going to plot these two vectors that we generated on top of the original data. So this vector right here is that first principal component, and this is the second principal component. And you can see that I've also scaled them by the explained variance. So the first principal component, this one right here, is much larger than the other principal component, and this one's pretty small. This is the second component is small, and it makes sense. You can see the relationship between these two variables and see that most of the information is along this first principal component axis. Most of the information is contained in this direction. That's the primary relationship between this data. Now, what's captured by this other component is actually anything that's along this axis, which is just basically noise. So the only thing that's really interesting to us here is all contained along this axis. That's our principal component. So what we can do here is actually transform the original data using the PCA model into a one-dimensional data set. So I'm going to make a new PCA with a single component, fit it on the data, and then transform the data using that fit. So you can see that the shape of the original data set was 200 by 2, 200 rows, 2 columns. And the shape of the transformed data is 200 rows, 1 column. I've reduced the dimensionality. And let's plot these two data sets together. And you can see I've got the original data, and now I've got the data that's been transformed by this principal component analysis, and all of this data is along this first principal component. It's all the important information is captured by that transformation, and we actually don't really need the noise.